So, welcome back. We are now ready to get started with the main seminar of today by Bartosz Kwas from the University of Białystok. And he will be talking about Groupoid Banach algebras.
Thank you. Is my micro on? I think so. So thanks for having me again here. And today I will speak about these things, and the talk will be based on two papers with two guys from Białystok, Krzysztof Bardarin and Andrzej Maki. And okay, without further ado, so I think that everyone in this audience know this world of sister algebra, so I'll start with that. So we have this category of sister algebras, say, and star homomorphisms. So what I want to do, I want to embed this category into this much larger category of, say, algebras. And morphisms are contractive homomorphisms. So everyone knows that star homomorphism is contractive, but for sister algebras, if you have a contractive homomorphism between two sister algebras, it has to be star homomorphism. So for homomorphisms between sister algebras, being contractive is equivalent to being star preserving. Does that need an explanation? I see Tristan is thinking, or maybe he's just. I mean, so one proof, so star homomorphism is contractive. This falls from spectral blah, and the other. So look at, you can always think about unital homomorphism between two sister algebras, and unital sister algebras is spanned by unitaries, and unitaries are just invertible contractive elements, and contractive homomorphisms will present those. So this is the kind of the simplest proof. I mean, I know several different proofs, but I guess this one is. So this category, I will soon leave this one, but yeah, I just want to say some motivation. So motivation for all this black came from Chris Phillips, who started this program of this, trying to generalize all this. I mean, some of these constructions to what is called now LP operator algebras. So roughly speaking, these are just operators, algebras of operators that you can represent on some LP space. Some LP space, meaning this is just a space associated to a sum measure for some P. This is small p. Usually people ignore this, but I want to keep it. And so now this become like a business, or like a number of papers keep on appearing on these things. And there is a version of it which is called like symmetrized, because these are just, there is no star in this thing. So people also consider like star version of it. This is called, these are called symmetrized thing. So basically the proofs for this and for these are the same, but you just run out the same argument. So we kind of introduced, so to have all this in one picture, we introduced. So these guys are kind of, but you can represent them on LP spaces and on the associated dual space. So you have also like so you have this Helder's conjugate number. So then you can also have a star. But for me, star is not important, and we can all embed this into what is not. This is a capital P. This is LP operator algebra. And you can do it for any subset of these parameters. So for any subset of these parameters, you can take the operator algebras that can be represented in all P spaces with parameters from this P. So of course, sister algebras are those that can be represented on L2, because L2 is just a Hilbert space. So the idea here was like to tilt a bit the Hilbert space, so move from 2 to somewhere else. That was kind of the main idea. But what I would like to tell you today is that I believe, so this is like a really nice framework where you can prove some things, in fact, like in the same spirit as for sister algebras. But in fact, there are some guys living outside, and I will just give you one, but this is a good one. So I will stick to that one. So this is what Akila told you. So this is this transformation thing. So we'll start with, so there is a consensus about what is a Banach algebra cross product. So we'll start with that. So yeah, so let this G be a discrete group, say acting on a compact space. Okay. So we have this space A1. So this is the space of functions from G to C of X, and with norm given by the sum. And this is the usual supremum norm. So A of G is a function, continuous function on X. So this is a perfect Banach space, and we equip it with convolution product. So if that was a group, then I would write something like that. But since I need to incorporate the group action, maybe I will call it theta. So then I need to use my left or right hand. I will use my left hand. So I will implement this action. So I will write this theta here, theta h. This is a function multiplied pointwise by the function. So with this thing, this is a Banach algebra. In fact, you have also the star. So what the star should be, because I use my left hand, so that will mean, I guess, something like that, and I need to compose with theta G inverse. But I will focus on that. So this is the Banach algebra cross product. So this is a star Banach algebra. And why, let me say just one word, why this is the right definition, because we have, for instance, this one-to-one correspondence between representation of this Gaussian covariant representations. So yeah, I was not sure. This space with this 2 operations or 1 operation, whatever you prefer. So representations, for me are, like I said, contractive homomorphisms. So representations of this L1G are in bijective correspondence with covariant representations of the action. So what do I mean by that? Maybe I will just simplify. So I will mean that here that I mean like just this contractive. So representation here. This is a Banach space, and these are bounded operators in Banach space. So this is like a unital contractive homomorphism. And covariant representation is what? So I need a representation of my group. So let me call it T, because I want to use U for something else. So this is just a group homomorphism from G into the group of invertible isometries on the Banach space. And I want to have a representation of my algebra C of X. And I want a commutation relation between these 2 guys. So I want for any group element G and any A in C of X, I want this to be, say, what do I want? I use left hand, so this means I want something like this. I want to move it here. So this is universal in this sense. So for instance, if you take E to be Hilbert spaces, so if you restrict just to Hilbert spaces, then you will get like this, if you complete, like Aquila did, using just representation where H is a Hilbert space, you will get the full C-star cross product. So this space can be served as a this algebra can serve as a basis for other completions with other things. So if you take E to be Hilbert space and you take the largest norm for these spaces for Hilbert space, you will get a C-star algebra cross product. If you take E to be LP space for a fixed P, then you will get what is called LP cross product and all this blah, blah, blah. Okay? Yes, here I just consider Banach space, and this is a good example because here there is like a consensus. What should be the Banach space, Banach algebra cross product? So I believe this is a good guy for this reason. Let me maybe present it in a groupoid way, like Aquila did. So we can view this space L1G. So previously I viewed them as functions from G to C of X, but in fact I can take these two guys on equal footing. So I can view this as a function, as functions from G times X to C, which are continuous. And here I put a product topology. And such that we have this norm becomes what the norm is. The norm is now, the norm is now what? The norm is I take the sum over G and then I take the maximum, so I take the supremum. So this is my norm now. And then this product, this funny thing looks like this. In this picture, it looks like this. So I have this to evaluate in point K and X. And this is just boom. So this is just convolution product. And you should write. I mean, so the thing that this converges, so I didn't write it. So this is L1, so this means that this converges, so this is finite. Tells you that everything works. So this is convergent, everything works, yes. So this should immediately ring a bell and recall this transformation groupoid. So this is this et al. Groupoid that Aquila introduced. With the unit space, so we identify the unit space with X. Formally, this is like this layer. One is the unit element in the group. And we have this composition law like this. So it's like HX. So we can compose them to GHX if Y is theta HX, because this is what Aquila taught us, that if you have this, so you view this pair like HX as this arrow. So if the arrow ends in a good point, so this is Y, then we can compose it with G to get a point. So we view these pairs as a pair starting with, so the source is X, the range of HX is, okay. So the inverse is something, I don't care much about the star. So one more thing, so we can view this L1 GC of X as a completion of CC of this groupoid, right? So there's this star algebra CCG of X. When I view this as a groupoid, now we can see that it sits as so we can identify it in fact with CC of GC. I assume X was compact, so this is this. This sits in a dense way in this thing. So we can view this L1 GC of X as a completion of our groupoid algebra in some Banach algebra norm. I mean exactly this one. So this is this nice picture, this more general picture of groupoids. I mean, strictly speaking, this is a bit different picture because groupoid will not remember the group. It will remember the orbits of the action. It will remember a lot about the action, but not the group. So if we want to like emphasize what is the difference when we pass the groupoid, so when we forget about the group, so the difference is that you can express it in terms of bisections. So look, for every G, this layer is a bisection. Bisection is this set where the range and maps, the source and range are injective maps. So once I fix G, and if I tell you X, then you can figure out what is the range. So this is, and if I tell you the range, you can also figure out the source because all these maps are invertible. So this is a bisection. This is an open bisection. So this is how I denote the open bisections. So this is the family of all open bisections. And this is a specific family of these open bisections coming from this group. So in fact, we have this mapping. So bisections form an inverse semigroup, if you know what that is. So this is just a group of a semigroup homomorphism. And this is kind of, I think of it as a grading. So the groupoid forgets the grading, so you don't have this, but this might be important later on. Okay. So let me now pass immediately to groupoids. So for me, this Carly G is always a tau groupoid. So this means that range and source maps. So this is, I think, what I've learned some years ago from Tristan, that these are just, you can save it. But these maps, I mean, X is the unit space. Locally compact Hausdorff unit space. So if you assume that this space is open in G, then this is equivalent to saying that these are locally injective. So if I just assume that these maps are open from G to G, then this will mean exactly what Aquila said, that these maps are local homeomorphisms. So this is a very quick way of saying that something is a tau. Okay. So do I need to say more about these groupoids? Because I can say something, or I can pass immediately to completions. So do you want me to recall anything about the tau groupoids at the moment? This is not that obvious, but you can show that this unit space is open in G if and only if these are locally injective.
How do you mean that?
Usually what people do, usually people assume that these maps are, even not in a non-tau case, they usually assume that these maps are open onto X, because this is a condition required for having the Haar system. But if you, so assuming that the unit space is open in G is equivalent to local injectivity here. So yes, so writing that these maps are open, I mean like this. These are open like this. If they are open like this in particular means that their range, which is X, is open in G. And these are open maps. You're welcome. Okay, so I will just go to the definition that we've already seen. So we call just this. And sorry, I mean, Aquila said this is not very wise to use the intuition because these are not necessarily, maybe I should stick just to Hausdorff case. So this groupoid is Hausdorff if and only if this X is not only open but also closed. So then this is just compactly supported functions. If not, then this space is just locally Hausdorff because these are just local homeomorphisms, so everything is local. And then we define as the span of these functions that leave open bisections, because open bisections are Hausdorff because they are homeomorphic to something on X, which is Hausdorff. So these are spanned by all these guys. Okay, and we have this convolution product here. We should say kappa maybe. It's like A of gamma, E of eta, gamma eta is equal to kappa. And we have a star operation that I don't care about. Okay, and we want to complete it. So maybe as I'm running out of time, I will just start right away with a definition, like a first approximation of what we want to look at. So this is given in a second paper, I guess. So Banach algebra completion. I will denote it like this funny way. F is for historical reasons because these are called pseudo functions, and R is for kind of for representations. So this is my notation for an arbitrary Banach completion of the CC of G in some norm. It's just a notation, some norm. I will say that this is a GBA, meaning Groupoid Banach algebra. If two things. One thing is I want my C0 of X to sit in it. So C0 of X also, so this is locally compact. Okay, I wrote it. Embeds into this completion. And here I consider this space with the usual supremum norm. So should I write what it means, or is it clear?
And you mean like the canonical embedding?
Yeah. So maybe I should write it. So any function CC of X lives in here because X is a bisection, because everything is trivial there. So for these guys, I want this arbitrary norm R to coincide with the maximum norm. So I want canonical inclusion here, canonical embedding. And I want like a conditional expectation. So when we have these functions here, we can restrict them to X because X is sitting inside of G. So we may restrict it to X. So when the groupoid is Hausdorff, then all these functions are continuous and X is also closed and open. So if I restrict continuous maps to close an open set, I get a continuous map, but in general, these are not continuous. I mean, so what I want this to induces contractive. I want a conditional expectation, but in this non-Hausdorff setting, this is just a generalized expectation. So this is a map which is it is identity on this algebra, but in general, it leads me to a larger algebra. So I just consider bounded Borel functions. Okay. So this means that for any function now on my groupoid, I want that the restriction to the unit space, the supremum norm, is not larger than this norm. Okay, so these are the things that I want to look at. And in addition, I can define what it means to be reduced. This is reduced if I should give a name to this map. So this is conditional expectations. And it continues. So in the Hausdorff case, this just means that this is a projection onto C of x. And maybe I should stick to the Hausdorff case. So what does it mean that this is reduced? So what would you do? So in sister algebra, this means the same as saying that the conditional expectation, maybe I should call it somehow ER, if this ER is faithful. But what does it mean to be faithful for a linear map? How do you define faithfulness? I mean, how do you usually do that? For sister algebras, how do you do that? So you want not to kill all these positive elements. So any non-zero positive elements should be mapped. But in fact, this is what I've learned, and algebraists use this faithfulness. So our sister algebraic faithfulness is awkward because this is not the original faithfulness. So the original faithfulness means that this kernel of this thing does not contain any non-trivial ideal. This is the correct definition. So let me teach you that lesson. So I will not teach you much, but maybe at least this. So this means, maybe I will try to. So if you have an ideal in your Banach algebra, so this is what closed-sided ideal, such that it is contained in the kernel of this thing, this means it has to be zero. So there are no non-trivial ideals, and for sister algebras, you can express it using positive elements. But this is a good way which works even in purely algebraic setting. So this is why you say, faithfulness. Yeah.
Value one, let's say, AB is, if it's zero for all A in your algebra, then B has to be zero. That's sort of equivalent.
It's close, but I have to think whether this is equivalent because these conditional expectations in general, I mean, in this setting, this might work because this is very symmetric. But in general, you might need to assume something, maybe. Yeah. So, okay, so this is the end of the definition. So, example for you. So, groupoid sister algebras, are they in this class? So maybe I should slow down and not to try to say everything that I want, just to. So the full groupoid sister algebra, of course, is in this class. I mean, so you don't see it? I mean, sister algebra, you don't see it? No, you don't? So maybe then I should stick to the Hausdorff case. So sister algebras that are GBA are exactly the class of what you would call like exotic. Groupoid sister algebras. So sister algebra, so these are exactly those that sit between the reduced and the full groupoid sister algebra. So the reduced one has this expectation. And this is like the smallest completion where you have this expectation, and all others, all lying above, they also have to have it, right? So this GBA for sister algebras, this means, and there is a unique reduced sister algebra. And this is exactly what Aquila presented. This is the reduced sister algebra. So there is a unique, maybe I should write GBA sister algebra. This is the reduced sister algebra.
Just so that sister algebra, well, the reduced actually is sort of the smallest norm. It actually has the
yes.
Yeah.
Yes.
So does that generalize even to more general Groupoid Banach algorithm?
I mean, so we made it a definition. This is the
definition is faithful, but the question is produced small among all those.
So this is the proposition that I wanted to mention now. So for any GBA, I invented this like yesterday, GB. For any GBA, so in the sister algebra case, what do you do with how do you prove? So you can prove. Okay, maybe I will write it first. So there is the largest ideal such that this ideal is in the kernel of this expectation. So in particular, if you give me like any GBA completion, I can quotient it out. By this ideal. And this gives me a reduced GBA. So for sister algebras, you usually, how do you prove it? So for sister algebras, when you have this conditional expectation, you can use the Schwarz inequality and all this positivity blah to prove that it's like in GNS construction, that you have this largest ideal contained in the kernel of this linear map. Here we don't have any of that, but instead of using the structure of this groupoid, we can prove it like using functions, that there is always this largest ideal. So in particular, you can now say that your GBA is reduced and only if this largest ideal is just 0. And this is related to your question. I'm not sure whether it answers it. I mean, because we have plenty of reduced things in the Banach world. So there is not only one reduced Banach algebra, there are plenty of them. If you restrict to cis algebraic case, then everything becomes unique, but not anymore. Okay, and maybe I will immediately switch to these examples. So what should I use to erase things? Is the right thing? My favorite example, this thing, this universal Banach cross product is reduced. This is a funny thing because in the Banach world, you can be universal and reduced at the same time, like always. This is reduced. And this is easy to see. And more general examples, if you work with groupoids, you probably encounter the so-called Hahn norms. So Hahn introduced them in 70s. These are like auxiliary norms that are now used all the time. So these are norms on the general groupoid, and they are defined using your hands. So groupoid has left hand and right hand, so you use them. So the left hand is called the source map. So this is map induced. So this is a norm induced by the source. So this is you take maximum over your unit space, and then you take like a once norm, but using source. So you take only those arrows that start in X. And that gives me a really nice norm, Banach algebra norm, a reduced Banach algebra norm. I can use my right hand. So I can do the same with range map. This gives me another norm. They are not equivalent. And Hahn wanted to have a symmetric situation, so I didn't write the star operation. The star operation is like this. So the star will transfer this norm into this norm. So if you want to have a Banach star algebra, you better symmetrize this. So this is exactly what is happening here. So you have this one norm, which is the maximum. You take your left hand and your right hand, and you put them both on equal footing. And all these are reduced Yeah, this is I norm, but do you know why is it called I? So I will tell you, because Han in his paper introduced several norms. So this is first norm, then he has like I norm and I. But now people call it I. Maybe it should be called like H, because this is from H. Yeah. I mean, so he introduced this, and now it's called I norm. Yes, it should be one norm, in fact, because so these are reduced norms. So this gives you this. These norms give you three different reduced Banach algebras. This one is star Banach algebra. These are not. These are all reduced Banach algebras. So of course, I mean, you can see where it came from. So when you have a group, when you have a singleton, all these norms become just a one norm. So when X is singleton, so then groupoid becomes a group. And all these are just L1 on G norms. So they all collapse to this norm that you usually use. But also note that, where is the norm of my favorite guy? Is it somewhere here? It is here. So this norm is different. So if you restrict to this particular case of the transformation groupoid, the norm on this guy will give you a different algebra than these three. Because here first take sum and then maximum, and here you do first maximum then sum. So you have, like in this particular example of a transformation groupoid, you have 4 different reduced Banach algebras. Ooh, Helen is scared. So I will give you even more reduced algebras. No, so there are results, like for instance, this is what Chris Phillips proved in his one of first papers where consider these LP versions of Kunz algebras. So whenever your algebra is purely infinite, these algebras tend to be completely different, meaning for Kunz algebras, this is proved, so maybe I should stick to that. So for LP Kunz algebras, for different P's, there's like, the topological difference is like that there is no non-zero continuous homomorphism between any of them. And so we have this. This is also related to Aaron's question, or maybe my answer to Aaron's question. So for each P, we have this regular representation on an LP space. So we have injective homomorphism from CC of G to bounded operators on LP space of G. And on its Scheider basis, it acts like Akil presented. But in function terms, this is just a convolution. So I will denote it like lambda P acting on psi is given. So this is a function on G, and the A is also a function on G. So this is just a convolution formula. It makes sense, everything works. And this gives you an injective map. So this is embedded in here. And you can use it to define what is called the reduced LP operator algebra. And it will be reduced in this sense. So this is regular. So already here you see why like LP spaces are distinguished among all other spaces, because if you take a different class of Banach, your favorite Banach spaces, then you don't know how to define this thing. For LP, everything works nicely. I mean, if you take P to be equal to, you will get the regular representation of your sister algebra. And these guys, so I just like to view them as I complete this space in this norm. And it is the same as I could identify this with the closure of the range of this map in here, right? So this guy is reduced. This is reduced. GBA. And the example with Kuhn's algebras will tell you that all of them are different. For different p's, they're like really different. Okay. Maybe one more corollary, just to give you even more algebras, reduced algebras. So if you have reduced norms and you take the supremum, so as long as the supremum is bounded, so it gives you a norm, this will be a reduced norm. So you can take any bunch of these reduced guys, take the supremum of their norms, and get a more reduced guys. So let me maybe state it. So this is for this. So you may take the subset of parameters, not just one parameter, and then define like the LP. This is now capital P norm, reduced norm. So this is supremum. In fact, this is maximum. So over all P's in P. Like this. This will give you the another reduced. Oh. So I think that's enough for these guys. Let me summarize something. So remark, C star of G, this F star of G, F star R, G, these are these Han algebras, the honest Han algebra, this one algebra, and also these symmetrized versions that I have not introduced formally of these LP algebras are all LP algebras for some P set of parameters. And this is what? This is F what? 2. F2. Very good. This is what? Oh, this is harder to guess, but it turns out that this is F1. And now this might be easier to guess. What is that? Close, but not quite. I mean, these are like very conjugate via stars. So 1 is conjugate to infinity. So this is. Okay, so what is this guy now? Yeah, so now you need actually like a set of parameters. So you need to like 1 and infinity. And this Han norm is the largest among all these norms, these LP norms. So whenever your P contains these two guys, then you end up with this norm. And this is the symmetrized version is just, you take just P and this Helder's conjugate thing. So in particular, the Han algebra is a particular example of this, where P is equal to 1. So all of these are of this form, but not our favorite guy. I mean, this guy applies only to the transformation groupoid, but it is not of this form, like at least not on the nose. So this is a good class, this LP, but still we need these things. And so what is the difference between this LP and our favorite guy? So remember, I told you, and I've erased it, but this groupoid forgets about the grading, and here we have like a grading, this G. So this algebra remembers this G. So if we want to do that, we need to introduce one more definition. Sorry about that. but this is the last one. So we introduce like S-graded Banach algebras. So these bisections in the groupoid, they form an inverse semigroup. So we want to pick one. So here this was the group G. But in general, this would form an unital inverse semigroup covering G. So we want these elements of this S to cover the whole groupoid. Then we say that groupoid Banach algebra is S graded if for any bisection and for any guy in here, this norm is, so I could write it like this, is not greater than this norm, but in fact it follows from previous assumptions on this GBA that in fact we need to have then equality here. So this means that it is as graded in this sense that all these spaces coming from this bisection in this fixed S, they embed isometrically into this. So if you remember, I just assumed so far that the unit space, the function of the unit space embed. Here I kind of also assume that also spaces coming from some inverse semigroup that covers this thing are embedded there. And there is a universal S graded GBA. I call it just Fs of G. This is easy to define. I could say a lot about it, but I don't have time. So there's like a universal. So in general, there is no universal groupoid Banach algebra, but if I fix this S, I can define the universal S-graded groupoid Banach algebra. And this, our friend, is exactly one of those. Where I treat here this G as I identify them with these corresponding bisections. Good? Oh, I still have some time. So one more important and interesting thing is that the difference between this LP and this guy, which is not LP, is that so LP operator algebra, so these LP spaces are like close enough to Hilbert spaces, so they smoothen the grading. So that is why, for instance, for sister algebras, when you consider like algebras given by generators and relations, usually these are like partial isometries. So these partial isometries give you the grading usually because they form an inverse semigroup, like a natural one. But in the end, you don't need to remember this inverse semigroup grading because sister algebra norm kills this information. So it is not important. And it turns out that this is the case for all this LP block. So this innocent theorem that I will well know is really important when you want to like define things in terms of generators and relations. So any representation psi on this universal S-graded algebra on an LP space, so this is any LP space, factors through this Hahn norm. And Hahn norm, I didn't say it, maybe I should. This is, yeah, so all these norms are graded by all bisections. Because on any bisection, so if you take A, if A lives on a bisection, then there is no sum. This is just maximum. So these norms are as graded by any bisection. And therefore also this one. So any representation, if you consider a representation of this as graded groupoid algebra on an LP space, so if you embed it into LP operator algebra, then this norm induced by this representation is not greater by this I norm. So for instance, in a non-entire setting, when you define your groupoid C-star algebra, this is what people usually do. They consider all star representations bounded by Han norm because they needed a bounded, they needed like a bound on it because there is no bound given there. And for a tau groupoid, because of this constant KF that Akila talked about, usually people define groupoid C-star algebra as using the maximal norm. So then there is a question, do these two definitions agree? So if you take all star representations bounded by I norm, are they the same as when you consider the maximal C-star norm? In other words, is every C-star norm on CC of G smaller than this thing? So this theorem tells you that. It says even more, it holds for all LP operator algebras. Because on the norms, this is always not greater than this norm coming from all bisections. And if you choose some set of bisections, this might be even greater. So this theorem says that choosing any grading, you can, when you push it to the LP operator algebra, in fact, you can go below the Han norm. So the slogan is that LP operator algebras do not see degrading, which is kind of cool when you want to kind of generalize this theory of C-star algebras to this setting. Yes?
You can only take that all bisection.
Yes.
Then it seems to me that pretty much all of them are graded in that sense, except for the L1 norm. Is that right? Like virtually everything I can say there would be graded except that L1. So
Which L1? Because I have now many ones.
we can just take like on the CCFG, you just take literally L1 of that.
L1. So this won't be as graded because here I take bisections, open bisections. So so LP operator algebra because of this will be graded. But here is this example is this example tells you that the grading is important. So this is an important example because there is a consensus that this is the right Banach algebra cross product. And for having a groupoid model in this general Banach algebra world, you need to add this grading. And this is not all bisection. This is like a fixed G. So you want to play, I mean, it depends on how general your theory you want to have, but I believe that this is the right thing to add in general when you want to study Banach algebras to add this grading. If you care only about LP operator algebras, good news, you may forget about the grading. If the representation is bounded by some grading, it will be bounded in any grading. In fact, it will be bounded by the Han norm. And last theorem maybe, so what we can prove with this where is my notes? I've lost it. No, it's here. So you can prove many things, but let me just give you a sample. Assume G is Hausdorff. Then the following are equivalent. So one, G is minimal and topologically free, which when I assume that G is Hausdorff is just effectiveness, you probably know what is that. And this is equivalent to that every reduced, and here I also need grading, but by some grading, so I will just write graded. But here you may choose any grading, so it does not depend on which S you pick. Empty? S cannot be empty because S has to cover G. So this is simple. as a Banach algebra. So this means that there are no closed two-sided ideas, non-trivial. And so this is related to minimality, but also, yeah, if I want to have if and only, then I need to add that this algebra that sits inside here is maximal abelian. Banach subalgebra here. And this is the same as one of them has these properties, and all of them have. What else do I have? I could continue go on like forever, but let me just. So this is the same as the Han algebra is simple. No further conditions. So when topological fitness is actually needed here without any five, like these extreme cases, like there's these two guys are extreme because they behave like they would be amenable. So I could also add these guys here. So I don't know, like reduced one group is simple. 6, the reduced infinity group is simple. And maybe I will stop here. I will just add one more thing. Ooh. Yes, yeah. So that is why I mean I could phrase it in a different way, but I wanted to have it like in a nice way. So all these things could be like considered separately, and I could say more, but I don't have time now. I just want to advertise, right? So this is just if the above hold and G is locally contracting, then all the above algebras are purely infinite. So there is a notion of pure infiniteness for Banach algebras. In a unital case, this is like really well established, but you can define it in a more general way, and this is it. So do I have a minute or not? Oh, 3 more minutes. So is there any question? Yeah. This is the standard notion introduced by Claire Anand Haramandarosh. No, this means that you have this kind of open set that you can put one dynamically. I mean, you can always shrink it. So you can produce these projections, infinite projections. So this is a standard notion. Okay, so like, of course, if G is amenable, so for pure infiniteness, it seems that topological fitness is needed. For simplicity of this reduced, it is usually not needed. But if G is amenable, then you could add 7 when all these FP G is simple for some hence any P. And I kind of wanted to talk about non-Hausdorff case, but I didn't have time, but I can say this thing here. So there are like really nice new papers appearing on this subject in the context of sister algebras, of this vanishing of the singular ideal that Aquila mentioned. And there are these nice theorems in this paper of Briggs, Gonzalez, Hume, and Lee. I hope I didn't forget anyone, about this Hausdorff cover of the groupoid. The theorem that they proved actually works in a general setting of functions. You can apply it to Banach algebras. So let me just state it. So you assume that it is like finitely non-Hausdorff, which means that any point that I take, it cannot be separated with at most finite number of other points in the groupoid via open sets. This is what I mean by saying finitely non-Hausdorff. So they found this criterion for vanishing of singular ideal for these finitely non-Hausdorff groupoids. But I claim it works in that generality that I can apply it here. So the condition characterizing this vanishing in this setting, yes. So in this paper that I mentioned, it is called not as zero, but there is a recent paper of Jeremy Hume, who has really nice, more closer to groupoid conditions characterizing this. And then I claim that I believe all of these remain the same. So I may go beyond Hausdorffness with these nice conditions of Jeremy and still get these things. So in particular, last week, there was a paper appeared by the student of Nora Shakas. So I think he's Norwegian, so I'm not sure. Maybe I will just write his name instead of pronouncing it. So this is related to his paper. So suppose he also considered the Steinberg algebra. So if G is ample, you may consider also this purely algebraic thing, which is called the Steinberg algebra. And that all these conditions are also equivalent to the Steinberg algebra, the purely algebraic object, Steinberg algebra, with coefficients in complex numbers, of course. This is, I think, the right notation is simple. And this is related to the paper of this Jussi Åker, if he's Norwegian, or I don't know, Josiah Acker, if he's not Norwegian. Because this non-Hausdorff finitely, I mean, so there's this class of contracting self-similar actions where they groupoids exactly fall into this class. So he showed that in this paper, I mean, he discussed other things there, but one of the results is that the Steinberg algebra is simple if and only if the reduced sister algebra is simple. So I have more because this is equivalent to also to all these other conditions, because this groupoid for the locally the groupoid for the contracting self-similar action is amenable, and it is finitely non-Hausdorff. And I think that's even too much already. So thank you.
All right, questions for Bartosz?
Is your definitions of amenability?
It's the same. So the definition of amenability, I mean, okay, so
Because for ethyl,
I mean, so here maybe I should, if I am like really feeling secure, I should add second countable here. Because here I use the result of Martino Lupini and Eusebio Gardella, who assumed this, and they needed it there in their proof because they kind of generalized this Renault disintegration theorem, which uses this separability assumption. But this is the same definition, the usual definition. You just replace your.
So you mean that the reduced and the full cross product are same?
No. So this is amenability of the groupoid. So you have this like quasi-invariant mean or something. There are plenty of equivalent phrasing of this. But this is the standard notion. And in the paper of these four guys, Briggs, Gonzalez, Hume, and Lee, I hope these are four guys, you can see that they've shown actually that the equivalences between all these things, and they also introduce some other amenabilities in this non-Hausdorff setting. But in the second countable setting, all reasonable definitions, they agree. So that's the moral of the story.
So I just have a quick question. This thing about G is topologically free under these conditions. If you were to just look at G being topologically free, would that be equivalent to the C0x sitting inside FR of G as being what, aperiodic, or in some sense?
This would mean that you have the intersection property. So this would mean topological freeness alone would mean that in this inclusion, that this algebra detects ideals in this, which means that if you have any ideal here, which is non-zero, then it has to intersect this thing.
Okay. But okay.
And I could also express this topological freeness using full LP operator algebras, but I have not defined them, so I prefer not to do it.
Right. Fair enough.
But yeah, this is like, yeah.
Because I didn't.
Yeah, so you have this intersection property, and sometimes, so topological freeness gives you this intersection property for all reduced. And if you phrase it so this would be like a periodic, whatever that means in this setting, because
You don't have a star, but yeah.
yeah, this would, so for sister algebra, this is exactly this.
Mhm.
And topological freeness in general for the groupoid is defined like that. You take the isotropy, you cut out the unit space,
Mhm.
the isotropy, you demand for this to have empty interior. And this is weaker than effectiveness, which tells you that the interior of the isotropy should be the unit space.
Right.
So when G is Hausdorff, these two are equivalent. But for non-Hausdorff setting, this is also my mission to make people realize that effectiveness is not a good condition. So topological freeness is the right condition there.
So I know what it means for sister algebra to be purely infinite. Maybe you said this, but what does it mean for?
No, I mean, I didn't give you a definition, so maybe I will try. So maybe let me start with unital case, because this is the most well established. So if you have a unit in your algebra, so this is purely infinite. I guess you need two things. So you don't want this to be just complex numbers. And then this is the condition that appeared, I think, in the first paper of Kuntz, where kind of pure infiniteness was born. He actually used this condition in the sister algebra setting. So for any non-zero point in your B, there exists like two other guys such that X, Y, and Z is 1.
Right. So you need simplicity for that, right?
Yeah, so this is the right notion for simple algebras. Yes. So I don't have a good notion of pure infinity in a non-simple case. So that's a good comment. Yes. So I believe I have a good notion of pure infiniteness in the simple case.
I see. And you have this recent paper with Ralph and Akshara where you define this type semigroup and then characterize pure infiniteness and stable finiteness of groupoid algebras. Does something similar work here?
I mean, I have not studied that, and I think you would encounter some problems. I mean, so this is not like I'm saying that this should not be looked at. I'm just saying that I have not looked at that, and this might be difficult because there you kind of, I mean, so basically we did not actually use Kuntz semigroup, but I mean, it's hard to kind of imagine the analog of Kuntz semigroup in this Banach algebra setting. I mean, this would be hard, right? You don't have positivity or anything. But no, I mean, my answer is I don't know.
Okay.
I don't know.
Thank you. And maybe one last question. So, is there some sort of Cartan Renault reconstruction theorem? Like, is there a notion of Cartan subalgebra? Because you mentioned like maximal abelian subalgebras and effectiveness.
So yeah, I could answer it. Not yet. This is tough for you, but I mean, if you want to this decomposition, you see that I showed you like I don't know, bazillion of reduced algebra associated to 1G. So this reconstruction, what do I want to say? No, I believe that this reconstruction should work if you phrase it in a nice framework. But this is not studied. I mean, at least I don't know. You mean rigidity? Yes. Yeah. I forgot to say about that. So one good thing about this LP blah is that when P is different than 2, this is what I wanted to say. Yeah, thank you. So these LP spaces are much more rigid than Hilbert spaces. So for instance, I think that in this paper they deal with ample groupoids, but I believe this holds in general, and I think they are writing it up. So whenever you have so this algebra remembers G when P is different than 2. So you can reconstruct G. So it's even better than Cartan inclusion. Yes. Yeah, I was thinking now like more in general Banach algebra terms. Then it's like, oh, I don't know what to do. But in this case, you don't even need anything. You just take your algebra and you see the groupoid.
Thank you.
Other questions? I had one question. How much work would there be in developing a similar notion for like Banach star or Groupoid Banach star algebra?
So in this endeavor, I kind of tried to ignore the star, so I didn't say much. But if your algebra is star and you have a representation, like a good representation, which something which has a star, but usually automatically the stars coincide. So that was enough for me. I mean, I kind of seen this business with this symmetrized. I don't have them. Oh, I do have them. With this symmetrized. I mean, to me, they're kind of artificial, but maybe I'm just too ignorant to understand. I mean, my feeling was that people are so used to stars that they don't want to forget about it. But for instance, this theorem applies to this because this is an LP operator algebra. So this applies to this symmetrized version LP. And for Banach star algebras, if you want a star, then I don't know what to do with it, to be honest. But it doesn't mean that you can't do anything. It just means that I don't know what to do.
If there are no further questions, then let us thank the speaker again. See you next week.
Thank you.
If you have any difficult, let's do this later. But a little bit often, yeah.